So, as we saw in my little video clip, Einstein explained gravity as a curvature of space, as a dent in space. He came up with this 100 years ago, what we call general relativity. This was 10 years after E equals mc squared, which is part of special relativity. This is called general relativity, where all matter, planets and stars and moons and galaxies, they warp the space around them. And anything in their vicinity will follow that warpage of space, including light itself. And this was first demonstrated famously in 1919 by Sir Arthur Eddington, who went to Africa during a total eclipse and showed that the stars that he could see, okay, in the background of the sun there during the total eclipse, those stars were sort of shifted out of position. Why? Because their light was passing around the sun where the sun had bent the space around it, and that curvature of space caused the light from those stars to be bent slightly, and that made it look like they were out of position by a very, very tiny amount, but exactly the amount that Einstein had predicted. And from that point on, Einstein was world famous. Light behaves the same exact way as a baseball does. Now, if I throw a baseball across the room, you can see the curvature due to gravity. And you think, well, light doesn't behave that way. A laser beam travels in a straight line. But if I threw a baseball at the speed of light across the room, would you notice it bending? No, you wouldn't. There's just not enough space there, not enough distance to notice the curvature. But light behaves exactly the same way a baseball does. We can actually slow light down. I mean, light slows down when it goes into pool water, for example. But we can actually slow it down an incredible amount with a substance called a Bose-Einstein condensate, to the point where we could slow light down enough that it would start pouring out of a flashlight the same way water pours out of a hose. It wouldn't behave any differently. Oh, then speaking of that, then the light itself is going to follow the curvature of space just the way a satellite would. So here we have a little animation, a little graphic here showing a gravity well, a gravitational well, a dent in space. That's what a black hole is. Now, speaking of wells, if I fell down a well, and let's say I have some kind of hook, I can on a rope or something, I can throw it out of the well. If the well is 10 or 12 feet deep, I'm going to be in pretty good shape. I don't have to throw that hook very far up to get it out of the well and maybe pull myself to safety. But if that well is 30 feet deep or 40 feet deep, I'm in trouble because I'm going to have to throw that hook at a much faster speed to get it out of the well. Well, the Earth has a gravitational well around it, its own dent in space. And to get something away from the Earth, whether it's a baseball or a satellite, you have to throw it upwards at 11 kilometers per second. Now, that's incredibly fast, of course, but we can do that. Human beings have spacecraft like the New Horizons going to Pluto. It is traveling at that speed, or actually higher than that, because it had to reach that speed to escape Earth's gravity and have the momentum to continue. But that's Earth's gravity right now. What if Earth was denser than it is now? Well, then the surface gravity would be greater, and it would be even harder to get a rocket away from the Earth. And if you eventually crunch the Earth down to the size of a grape, to get away from that grape-sized Earth, instead of traveling at 11 kilometers per second, you would actually have to travel at this number, 300,000 kilometers per second, which is the speed of light. So even light itself could not escape from that grape-sized Earth, which would make it a grape-sized black hole. Even in a well, okay? If you just imagine throwing a baseball, if you don't reach that right escape velocity for the baseball, it's going to come back and hit you on the head. Well, if you're inside a gravitational well of a black hole, and you take a laser beam and you shine it upwards, guess what? It's going to come right back down on your head. That laser beam, that laser light, the photons will go up and actually just fall right back down. By the way, you're in a lot of trouble at that point if even light can't escape. So that's all a black hole is. It's a gravitational well so deep that even light is not fast enough to escape. Any massive object then can become a black hole if it gets crunched down enough, if it gets dense enough. That's the key. Black holes can be little, black holes can be big, but they're all incredibly dense. Here's a nice little artist rendition of the curving space around a black hole. We've seen many examples of this in space where objects warp the space around them and you get these interesting blurs of distant objects in the background. Now, I said a second ago that black holes can be small, right? Well, check this out. This is the Large Hadron Collider, one of the most complicated, complex machines mankind has ever built. It's a particle collider in Switzerland and France. Starts at CERN in Switzerland. Its purpose is to accelerate particles at nearly the speed of light and smash them together and basically see what comes out. Well, I don't know if it's going to be the LHC or something like it. And as you can see here, it's actually 17 miles long. It stretches, again, mostly under France, but it's underground. It's an underground tunnel. 17 miles long. And when those particles collide at nearly the speed of light, they're able to research new kinds of particles, such as the Higgs boson, which was their big discovery. But one of these days, whether it's the LHC or the next generation of particle colliders, eventually they're going to slam two particles together, and at that moment, it's going to become so dense, they will create a black hole. We will eventually create black holes in the lab. Not to worry, these black holes will be microscopic, and thanks to something called Hawking radiation, they will evaporate immediately. So no danger there. But who knows what will happen hundreds of years from now if they're able to master creating black holes in the lab. So what happens if you fall into a black hole? You'll have to wait for part 2 of this lecture to find out. Thanks for listening.